Hi, this is Zhuojia Shen from the University of Rochester. Today I'm going to present our work on fast execute-only memory for embedded systems. This is joint work with Komail, Dharsee, and Criswell. Code disclosure attacks launched by a remote attacker are dangerous, as they allow the attacker to steal intellectual property such as proprietary code, or to find gadgets for code reuse attacks like return-oriented programming. The situation is even worse on embedded IoT systems like home security cameras, smart door locks, and smart routers. On the one hand, these systems have the same internet connectivity as desktops and servers, which is brought by the rapid expanding of IoT. On the other hand, these microcontroller-based systems lack protection usually seen on general-purpose systems, making them an easier target for remote attackers. Recent research has focused on execute-only memory, or ZOM. Execute-only memory is memory that only allows instruction fetching, but disallows reading or writing. It is therefore a best fit for defending against code disclosure attacks. However, such simple and effective defense is not natively available on ARM embedded systems. There are previous ZOM approaches, but each of them has limitations. PicoXOM, the state-of-the-art for this purpose, realizes ZOM on ARM embedded systems, but incurs significant performance and code size overhead as much as 20%. Another attempt is PZROP, but it only supports flash memory on ST microelectronic devices. All other ZOM solutions require a memory management unit, which is also absent on ARM embedded systems. So here we present PicoXOM, a novel ZOM solution for ARM embedded systems which uses ARM's debug support to achieve execute-only memory, works on the mainstream ARMv7-M and ARMv8-M architectures, and is efficient in both performance and code size. This is the outline of my talk. Before we dive into the detail of PicoXOM design, let's first take a look at the unique features of ARMv7-M and ARMv8-M architectures. These architectures support two execution modes, privileged and unprivileged. Bare metal software running on these architectures by default executes in the privileged mode for full device control. Although without a memory management unit that supports virtual memory, these architectures support an optional simplified memory protection unit that can enforce region-based access control on physical address space. Unfortunately, the MPU does not support the execute-only permission needed by ZOM, which is why we need solutions like PicoXOM. Finally, let's look at the data watchpoint and tracing unit, which is part of the ARM debug support. The DWT unit provides groups of debug registers called DWT comparators, and each DWT comparator can be configured for many functionalities like cycle counting and PC value tracing, but most importantly, each DWT comparator is able to monitor memory accesses to an address range. When a memory access falls into an address range monitored by a DWT comparator, a debug monitor exception will be generated and the execution will trap. On the other hand, if the access does not fall into any configured address range, the execution will proceed as normal and the performance will not be affected at all. Utilizing these unique features, we can enforce ZOM as follows. First, we set up write or execute by simply using the MPU. This is the same setting as many previous work where we mark the code region as readable and executable, read-only data as read-only, and all other memory regions as readable and writable. Second, we set up read or execute by configuring a DWT comparator to watch over the whole code region for read accesses. This way, illegal code reads will all trap and be captured, and ZOM is effectively enforced. However, we also need to prevent our MPU and DWT configurations from being neutralized, because MPU and DWT configuration registers are memory mapped. They reside in the system region and can be modified by regular load and store instructions. We can prevent neutralization in two approaches. One way is to run application code in unprivileged mode, as unprivileged code cannot access those registers in the system region regardless of how the MPU is configured. This would require us, however, to implement system calls to support privileged operations that the application could previously perform. The other approach is to write protect those registers by using another DWT comparator. I'm not getting to the detail of how each DWT comparator is configured, and we refer interested readers to our paper for those details. As we disallow read accesses to the code region, constant data embedded in the code region, aka constant islands, becomes no longer readable. There are two types of constant islands that an ARM compiler may generate. The first is load constant, which loads an irregular constant from a PC relative memory location into a register. The second is jump table jumps, which are used to implement large switch statements. Therefore, we transform the two types of instructions and remove their constant islands. Specifically, for load constants, we encode the 32-bit constant into two 16-bit immediates in the MoveW and MoveT instructions. For jump table jumps, we transform the instructions into a sequence of explicit instructions that do exactly what the TBB and TBH instruction does, but without a code read. This diagram shows the overall workflow of PicoXOM, where PicoXOM components are shown in blue. To use PicoXOM, embedded application developers simply compile their code with the LLVM-based PicoXOM compiler, and then install the generated PicoXOM binary onto their embedded ARM devices. On device boot time, the PicoXOM runtime will configure the MPU and DWT, and then transfer control to the application code. Now let's talk about the implementation of PicoXOM. We built a prototype of PicoXOM on ARMv7-M, in which the MPU and DWT configuration code is written in C, and constant island removal is implemented as an LLVM IR pass. Our prototype has one limitation because of the hardware. Specifically, ARMv7-M only supports up to 4 DWT comparators, and on our device, each DWT comparator can only monitor up to 32 kilobyte address range, sized and aligned by a power of 2. This hardware limitation makes our prototype only able to support a maximum code size of 128 kilobytes. However, we see no such limit on ARMv8-M because how ARMv8-M configures DWT comparators is different. In other words, we believe PicoXOM should work better on ARMv8-M. Moving on to the evaluation, here's the experimental setup we used to evaluate how PicoXOM performs. Specifically, we used an STM32F469 discovery board, which has an ARM Cortex-M4 processor we configured to run at 180 MHz. The board comes with 2 MB of flash memory, 384 kilobytes of SRAM, and 16 MB of SDRAM. It also has an LCD screen and a micro SD card slot, allowing us to run applications that use them. For benchmarks and applications, we picked 42 programs from the BEEBS benchmark suite that run longer than half a second, all programs from the CoreMark-Pro benchmark suite, 4 applications from the manufacturer ST Microelectronics, and 1 application called PingLog. We compiled and run each application and benchmark program with the baseline setting as well as the PicoXOM setting, and then compare their results. Here are the performance results on BEEBS. The two diagrams on the left side show normalized execution time of all 42 BEEBS programs that we picked, while the table on the right side compares PicoXOM's performance with MicroXOM on 33 BEEBS programs that they have in common. Basically, PicoXOM incurs an average performance overhead of 0.55%, much lower than MicroXOM's 7.3%. Note that a few programs exhibit a performance improvement. This might be because of the changed code region layout caused by constant island removal, or the DWT's alignment requirement, or both. On Komail-Pro, PicoXOM even achieves a negative average performance overhead with a maximum of 0.17%. The potential reason for negative overhead is the same as for BEEBS. And here are the performance results on the applications, with an average overhead of 0.02%. These applications show variances because they access much slower peripherals like LCD screen, SD card, and serial port. As for code size, PicoXOM increases the code size of BEEBS benchmarks by an average of 6.10%, also better than MicroXOM's 15.7%. Again, this is on the 33 BEEBS benchmarks that PicoXOM and MicroXOM have in common. Due to space, we are not showing individual numbers for BEEBS, and overall, PicoXOM incurs an average code size overhead of 5.89%, most of which is coming from constant island removal, as we transform load constants and jump table jumps into longer instruction sequences. To summarize, PicoXOM is a novel ZOM realization for ARM embedded systems. It is the first use of ARM debug features for enforcing security policies, and it achieves practically no performance overhead and low code size overhead as much as 7.93%. With that, I'm happy to take questions.